you know everything there is to know. Okay, can we go on? Okay. Point discontinuity. There's another word for that, point discontinuity. No, another formal word. But I never use it. Actually, I think it's having way too much fun over there. It's so annoying. Oh, a removable discontinuity. I know, it's because they removed that one point. How can we work? Sure. Sure. They're all learning songs. Oh no. Didn't copy on here. Seriously? Another one of these? Oh, good. Okay. This one. Yep, wonderful. Yay. Okay, 33. This was on your assignment last night, and here are the things. You're supposed to graph this. See if I can get creative. See if we can do this. And then this. What song is that? Does anybody know? Huh. Okay, well maybe you could read that, maybe you can't. But this says y equals x squared minus 1 all divided by x minus 1. We're going with it. Okay, so before we do anything else here, we should probably factor this out. So is there anything that you know of that can factor? Anybody? X squared minus 1 can factor, yes. So this becomes only happens when I'm recording. Okay, this becomes y equals x minus 1, x plus 1, all divided by x minus 1. So what do you expect to happen here? Are we going to have any vertical asymptotes? Are we going to have any jump or discontinuities at all? Okay, Casey, what are you expecting? So vertical asymptotes show up when the denominator is 0. At x equals 1?
Yes.
So somewhere at x equals 1, I'm going to have what?
A hole.
Yeah, a hole in my graph. I think that's correct. That's a good assumption. And we really don't know anything else, except we know we're going to have a hole there. So this is the point in time where you may want a graphing calculator. Trying to kind of verify this a little bit. But I would definitely write that down, that I'm going to have a hole in the graph at an x value of 1. Why doesn't it? I want to do the matching thing. Doesn't like me anymore. Okay, so let's try that again. Alright, that works. So x minus 1, x plus 1, and this is all divided by x minus 1. Let's see how this thing does with graphing. Oh, it does a nice job. So you see our hole in our graph there at x equals 1? Whoops. Okay. So this thing ends up being fairly linear looking. In fact, it looks like the equation y equals x plus 1, doesn't it? Like if you think about the straight line y equals x plus 1, and the slope is 1, and the intercept is 1. See how the intercept's 1 here and the slope is also 1? So it looks like a straight line with the exception of what? The little hole in the graph at an x value of 1. The point discontinuity. So what you need to be able to do here is to figure out in advance where the holes are going to be, where the vertical asymptotes are going to be. The rest of the shape of the graph is kind of a mystery to us at this point until later, when it won't be. So let's go to 35. See if we can do 35. Copy. Paste. Any factor needs to happen on 35? -1 all divided by x plus 2x minus 3. Jessica?
Well, I had a question on the last one.
Right?
How, by looking at the function, how can you tell the difference if it's going to be a hole or a vertical line?
I'm glad you asked. You could tell there's going to be a hole if the numerator and the denominator have factors that are canceling. So because there's an x minus 1 and an x minus 1 in the numerator and the denominator, and they cancel, that creates the hole in the graph. So if I have something in the denominator that doesn't have a factor in the numerator that cancels with it, then it will be an asymptote. So if we look at the next problem, 35, I don't have any numerator and denominator factors that are going to cancel. So I don't have any holes in the graph. But what I do have are two asymptotes. What are the values for x that create the asymptotes? -2 and +3. So I can make a sketch of this right now, and then we'll see how it compares to the real thing. So at -2, I'm going to have a vertical asymptote. Because it's where the denominator is 0.
I know, but that would 3 also be.
Yes, 3 is also a vertical asymptote. And there are also horizontal ones. And there's a way to tell. Sometimes you have slanted ones that are like diagonal. And you learn how to do that in pre-calculus. There's some little, it has to do with the degrees of the numerator and the denominator. We'll talk about that later though, or you might or might not. Now, like I said, the rest of this to you is kind of a guessing game, but let's see, what's my speculation? As x values get really small, what happens here? -10, that's a negative number, that's a negative number. Negative times a negative is a positive. So this is going to approach negative infinity. I'm guessing this is going to go, okay, I don't know. Let's graph it. I was going to guess, but I didn't want to be wrong on video. That would be embarrassing. -1 all over x plus 2, x minus 3. You want me to just take a guess? I'll just take a stab at it. Why not? Who knows? This is going to go somewhere like towards negative infinity, so this thing here is probably going to go this way. No, I don't know. I don't really know. What the heck? We'll see. What's going to happen?
That's really weird.
Yep. So, exactly why I didn't do this. So, do you see your vertical asymptotes on the graph there? Right there at -2 and at +3. What's wrong? It looks weird? So, in fact, there's also what kind of an asymptote here? A horizontal one at the x-axis. Funny. This kind of behavior that you see where it just slants down like that, all the way to negative infinity, is called asymptotic behavior. Asymptote, okay, let's give me there. Should we do the last one? Why not? So the last one is 37. Ooh, this one I can graph, I think. I don't know. So I have x minus 1 all divided by x squared minus 4. Oh, let's look at that one. Edit, paste. Is there anything I can factor there? Yes. So this is going to become y equals x minus 1. And then the x squared minus 4 is the difference of squares, right? This will be x plus 2x minus 2. So what should I expect to see? Any asymptotes? Holes in the graph? Okay, where are they, Xander? Okay. Should I try to entertain you by drawing this? Might as well. It'll be so fun. Okay, at 2 and at negative 2, I expect to see some funny asymptotic behavior. By the way, asymptotes have the dashed lines, they have arrows on them just like any other line. Okay, and then what's this going to look like? I bet, okay. Let's see if this works. I think that one's going to go like that. And then this one will, let's see, I have an x value of 1, I'm going to have a 0. So maybe that? This is a shot in the dark. Okay. What's that? You don't. Maybe. Okay, so let's see how we did. Oh no. This one?
Yes.
Press it again?
No. You press that twice.
Yeah, but it doesn't uncheck. See? I just want you to see how accurate this graph is. Okay, fine. What is it? X minus 1 over x squared minus 4. Ah! I wanted 100%. Okay, there you go. These are called fun functions. Because they're not like a straight line, they're just hard to predict. I can't believe I got that wrong. I really thought about it for about 1 minute. Maybe less. Hi. Okay. Any questions? These functions? Yes, you use your graphing calculator. The only thing you need to be careful about are the holes in the graph because they don't show up on your graphing calculator as well, and that you make sure you put the vertical asymptotes in. But it's just a guessing game, that's why you have to use your graphing calculator. Unless you make a table like we did, but you know that takes a long time. Gus? Yeah. Okay, doke. So now let's go through the what we're going to talk about today. Yay! Which is, I promise you, brief. Which is good. The rest of your buddies are doing other things. Now to the 2. There it is. 9-4. Okay, we're going to talk today about different kinds of variation that you have in the world. And the reason why we cover this in this chapter is to let you know that we're talking about things that are like universally related. So graphs that go up and down and vertical asymptotes and stuff. This falls under that. So the goal is to solve and recognize and solve direct and joint variation problems, and then also inverse variation problems. And we'll talk about the difference between each one. And I think you'll find that this stuff is pretty familiar. Remember from Algebra 1 that you have straight lines in the form y equals mx plus b. Right? That takes the form y equals mx plus b. These are called linear. There's a special kind of a linear function that's called direct variation. Direct variation is just a linear function, but its y-intercept is always 0. So the b is 0. That's direct variation. So if you ever see this kind of a function, that's a direct variation function. When the y-intercept is 0 and the slope is 1, we actually call that a special kind of direct variation function. That's called the identity function. This linear function y equals x is called the identity function. So the difference between linear functions and direct functions is a direct function is a special kind of linear function whose y-intercept is always 0. That's direct variation. You also have joint variation, where instead of depending on one variable, it depends on two. And then lastly is inverse variation, where it varies inversely, so it's like 1 over. And then the variable is on the bottom, the denominator of the fraction. We'll talk about all three of these. Here's the basic overview of them all. So if you want to just quickly write this in your notes, that there's direct variation in the form y equals kx. Joint variation is y equals kxg. And then inverse variation is y equals k over x. K is a letter in all of these, but it's a constant. So you know how you have y equals mx plus b? M and b are constants. They don't change once you figure out what they are. The slope and the y-intercept don't change for the given function. What changes are the input and the output, y and x. K is a constant of variation, which means that once you find k, you can always apply it to any problem. So k is a letter which stands for one number. Y and x are letters that stand for any number. As I said yesterday, whatever you do, don't look at your book in the section. It's kind of, it's just very confusing and complexity. It causes you to wander into losses. So one of the tricks is being able to find which kind of variation you're working with. Is it direct, joint, or inverse? And then we have to find k, figure out what k is. Once we find k, we can answer any questions that we ask us. This is very similar to solving linear functions. So remember, if you have 2 points and you have to write the equation of the line, the first thing you have to do is find the slope, right? And once you find the slope, you find the y-intercept, and you just plug it all in. Similar kind of process here. So for example 1, I have y, and it varies directly as x. Y is 12 when x is negative 3. Find y when x is 16. So here are your steps to this. It's pretty straightforward. You write down the equation in the general form. So what kind of variation do we have? Direct, joint, or inverse? Directly. So you write down your equation, which is y equals kx. Remember, I told you that k is a constant. So we need to find out what k is. Well, do I know some combination of x and y? Do I know some value for x that has an output of y? Yes, I know that y is 12 when x is what? 3. So I could say that 12 equals k times -3. And then I can solve for k. Well, what would k be? -4. Okay, and now I can answer the second part of the question. So the first part of the question was contained within this first sentence before the comma. Now I arrive and go to the second part of the question, which asks me to find y when x is 16. Now instead of writing y equals kx, what can I plug in for k? Well, I know what k is now. It's -4. See how this is like y equals mx plus b, but b is 0? So what goes in for x? Okay, I know it's early, but -4 times 16 is 64. And that will be my solution. Any questions? Not bad, huh? Well, there are only 3 examples, and this is the second one. What's different about this one is that what? Y varies jointly. So you have to look for the key word in these kinds of problems. So when it's direct, y equals kx. When it's jointly, that means there's more than one. Y equals k, x, z. Is that the one they use over here? Yeah, they do. We're good. And then we just kind of plug it in. What goes in where? Look for the first part of the sentence. I feel like this is just like so made up. It's not really real life at all. Okay, so we have to find y when x is 8 and z is 3. If y equals 16 when z is 2 and x is 5. So which part of the sentence am I going to use first to solve the case? The circled part or the underlined part? Underlined. In the circled part, shall we only have the x and the z? Okay. So then 16 equals k, which I don't know, times 5 times 2. Oh, we know 5 times 2 is 10. Divide by 10. K is 16 tenths, 8 fifths. Okay, we found K. Now we can answer the question that asks us. To find y when x is 8 and z is 3. So now instead of y equals kxz, I can write the equation y equals 8 fifths xz. And now I can plug in what I know, which is that 16, y equals 8 fifths times 8 times 3, which is 64 times 3. 190. Right? Because this is 64, 8 times 8. 64 times 3 is 128, plus 64 is 192. Believe me then. All right. No one's correcting me, so I guess we're good. 192 fifths. It's a sad world. I have to correct myself. Am I right? Maybe check it yet. Okay. That's why you're correct. All right. So, let's do another one. Last one. This is where y varies inversely. Inversely part? Inversely. As t. Oh, and it's r. R varies inversely. So r is going to equal, and there's still a k involved here, but the t now, instead of being adjacent to k, is divided by k when it's inversely goes on the bottom. So you can see here the k is at the top and the variable is on the bottom.
Wait, where did R come from?
R, they're just using different letters to try to mess you up. So you want me to show you how they work here? So the standard inverse one is that y equals k over x. But now they're telling me that r varies inversely. So r is like the y. And since it varies inversely as t, it means that this t is my other variable that's going to go on the bottom. My constant is still k. So now I have to find k. So I plug it all in. 18 equals k over negative 3. Find the value for k. Negative 54. And then you have to find r when t is negative 11. So now this becomes y equals negative 54 over x. And it's not y and x, right? Sorry, it's r and t. Negative 54 over t. We have to find r when t is negative 11. So this is negative 54 over negative 11. Negative divided by a negative is a positive.